Continuing our look at Mod 12, I want to take a look at what all of this is going to look like when it comes out of StatCrunch. So I have taken the 5 ordered pairs that were used in those scatter plots on the previous page, put them into StatCrunch, and then performed a linear regression analysis. You are certainly welcome to go ahead and do that at this point. I'm going to demo StatCrunch use for you in the next example, but you could go ahead and here's the list of values you want to use for your explanatory variable. Here is the list of values you would want to use for your response variable. The residuals I had put in as part of the linear regression analysis, so you wouldn't be putting those in. They would be something that StatCrunch gives you. So when you do this linear regression analysis, you get 2 different screens. This is the screen that shows up first. Click on the right arrow, and then you're given this screen, the scatter plot, along with the line graphed for you, that is the regression line, the line of best fit. So let's just go ahead and take a look at all the information that we're going to be given here. We've seen this screen before when we were calculating our linear correlation coefficient, so that is there. Our regression equation is here. And notice it's different from how an equation used to look in algebra class. If you remember that, you're probably used to seeing y equals mx plus b. So a few differences here. StatCrunch is not going to use the variables x and y. It's going to use whatever names you gave your columns that you chose for each of these variables. The other difference is, notice that the mx part comes second. You're given the constant first, which would have been b. Remember, that's the number that gives you your y-intercept. What you're given second is the mx part of that equation. This number that multiplies what would be our x is the slope of our line. And it is fine with me if you report your equations using those variable words rather than the column, if you use those column names rather than the variables x and y, that is perfectly fine with me. I did, however, in this case, since they were just var1 and var2, I went ahead and used y and x. So here's the equation of that regression line, rounding my values off to 4 decimal places. And remember, this is the line of best fit because it has the smallest possible sum of squared errors. Now, I've included here what that sum of squared errors is. Where did that come from? It came from this bottom section here. Sum of squared errors is given in the box that connects that column and that row. So this is where you can see the sum of squared errors for your regression equation. And notice that the individual errors or residuals show up positive and negative, just how I described in that last video. So for this point, 2, 5, here's that point. It's below the line. It has a residual, so its predicted value would be up here. And to correct that predicted value down to the actual value, you would have to subtract off 2.25, just rounding off to 2 decimal places. This next point, 813, well, here's that actual data. it has a positive residual because to correct this prediction, we would have to add 4.16 to get up to the actual data value. All right, last question here. What do we know about the sum of squared errors for the two lines that were given on the last page? So remember, it was this same 5 data points, but 2 other lines were drawn in. Neither one of them was the regression line. What can you say about the sum of squared errors for each of those 2 lines? Take a minute to think about it, pause the video, and then come on back. Well, hopefully you said exactly what I have here, that the sum of squared errors for each of those lines would have to be larger than this value of 41.77, because this regression line and every regression line has the smallest possible sum of squared errors.